Okay, so now it's recording. Good morning and welcome everybody to the lecture 4 of the course Quantum Theory in a Nutshell. Um, so yesterday we discussed the photoelectric effect and how the idea that Einstein put forward as light being formed by a beam of particles of photons uh, was necessary to describe the experimental data coming from the photoelectric effect. And after that, we described the Compton effect, which is essentially um, the phenomena that you see when you direct some light ray to a target, in this case, an electron. And when you do so, in order to describe how is the wavelengths that one measures for different values of theta, the scattering angle, you also needed to treat um, the wave as formed by a beam of particles, a beam of photons. So by applying the conservation laws of relativity that we did not did explicitly here, one could obtain how the wavelength of the scattered beam lambda is different from the initial wavelength lambda naught of the incident beam. So you see that this difference, it is really due to, this difference really depends on the angle theta of the scattered beam. So if you change theta, you change the value of this variation, which is called the Compton shift. Okay. So I see that there is something in the chat. So Mahmoud asked, what is the importance of the Compton effect? Well, for the time being, the Compton effect is just an experiment that, again, shows to us that light has has to be treated as a beam of particles. But of course, understanding how particles of light, or whatever particles you want to think about, scatter when they collide with some target is really a fundamental thing in order to describe physics of elementary particles. So when you go to these big labs as CERN, well, they have these particle accelerators. What they are doing there are just mashing particles against each other, and after this collision, these particles are scattered, and you have to measure the properties of the scattering in order to understand what was really what were the components of the beam. So scattering is a very important thing in elementary physics. But the Compton effect here that we described is very important in order to understand that you have to describe light as a beam of photons in order to get to this equation, which agrees with experiments. Okay? So it's really a very important conceptual thing. Okay, so there is another question. If energy is conserved, where does the energy difference between the incident and the scattered radiation goes? Could it be the kinetic energy of the target, the electron in this case? Yes. So this photon has, so let me put like that. This photon, it carries some energy, E gamma naught, and the scattered photon carries energy E gamma. So these energies are different, but energy is conserved. But what is conserved is not the energy of the photon, but the energy of the system. So before the collision, the electron was at rest. Therefore, it did not have a kinetic energy. So it did not have a momentum, okay? After the collision, the photon was scattered in this direction, but also the electron was scattered in this direction. So now the electron carries energy because it is moving, okay? And therefore, part of the energy of the initial photon was transferred to the electron in such a way that the electron was not at rest anymore, but it is moving. So the total energy is conserved, okay? Not the individual energy of the photon. Is that clear? Okay, good. Okay, so today I want to move on the history of old quantum mechanics, if you wish, and discuss a very important discovery due to Rutherford. And as you're going to see, for a couple of minutes in the lecture today, I will much more tell the history instead of writing equations. But the concepts are very important. So try to follow what I say. And every time we are going to try to connect with the concepts that we have learned in the previous days. Okay? So in the beginning of the 20th century, it was known that a particle that we now call the electron, we knew that it existed. Before I move on, there is a question in the chat. What happens if the change in lambda is 0? Okay. So going back to the Compton effect, if the change, namely if delta lambda is 0, it means that this term here is 0. So this term, the right-hand side here, is a product of a constant, which is non-zero. So the only chance that this product can be 0 is if 1 minus cosine theta is 0. In other words, cosine of theta must be 0. If cosine of theta is 0, it means that the scattering angle is just 0. The scattering angle of the photon. Okay, is theta measured in radians? So it doesn't matter. I mean, you can put in whatever way you prefer the angle. Okay. So be careful. It's not that if theta is 0, then the collision does not exist. If theta is 0, it means that the photon will not be scattered. I mean, will not have an angle, but you see that there will be a direction where I can detect radiation with the same wavelength. Okay? It's like this was a. It's like the photon just went through. Okay? Be careful with that.
Hello.
Hello.
Yes. This means the energy of the photon this photon can be still the same
Yeah.
after collision.
Yeah. So if lambda does not change, and we know that lambda is associated with the frequency, then the photon we have, since the energy of the photon just depends on the frequency, the energy of the photon will be conserved. Okay. So Elise is asking. Let me see. I think if lambda is 0, no initial energy exists. No, I mean it's just means that the electron. So you can think of this in the following way. Assume that you have a photon that was scattered by this angle theta, and now you're going to look at theta very, 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 very close to zero, okay? So if theta is very, very close to zero, and I can make it essentially, I mean, almost zero, then delta lambda will be roughly zero, okay? It doesn't mean that there was no collision. It just means that if you approach the angle theta to zero, then the Compton shift will be close to zero. That's all. Yes, this is what you wrote is correct. And you see that initially the photon has some wavelength lambda, and the initial energy will be h times c divided by lambda, which is non-zero. Okay. This question that you raised about ultraviolet catastrophe, I mean, ultraviolet catastrophe is a phenomenon that we discussed for the black body radiation. So this is not related to the Compton effect. You're saying that the energy will be infinity. No, be careful. What is zero is not lambda, but delta lambda. Okay? What Paul wrote is correct. So if delta lambda is zero, it doesn't mean that lambda naught is zero. Okay? It means just that lambda is equal to lambda naught. Okay? Yeah, so lambda equals to zero. I mean, this is not, this is a frequency that is infinity. So this is, I mean, this is something that is non-physical. Okay? Okay. Any more questions before I move to Rutherford? Okay. So moving to Rutherford, as I said, in the beginning of the 20th century, people understood that there was a particle called the electron, and that the electron had negative electric charge. So yeah, so there is a comment about the exercise. We can talk about the exercises in part 2 of the lecture. Okay. Okay. So the electron has a negative charge, and Thomson discovered the electron and tried to describe an atomic model. Okay. And by that time, it was known that the atom should contain electrons, which are particles with negative charge, and that the mass of an atom. So, Elisa, I see your question. I will take questions later, okay? It was also known that the atomic masses, namely the mass of an atom, was the masses were much bigger than the mass of the electron. So if the atom is composed by electrons, it must also contain something else, because the total mass of the atom is way bigger than the mass of the electron. And it was also known that atoms are typically electrically neutral. So again, if electrons are part of the atom, then the atom must have something else with positive charge in such a way that it is an electrical neutral thing. So we are understanding here that the mass of the electron is not enough to describe the mass of the atom, and that the charge of the electron is not enough to describe the charge of the atom. So Thomson proposed that an atom was composed by electrons, represented here by these negative charges in the drawing, and by a cloud of positively charged particles. And this cloud was freely to move in a region which was at the size of an atom. So you can think of these essentially as a ball that inside has some sort of gas of positive charges and also electrons there. Okay. This explains why the atom has a mass bigger than the mass of the electron, because you can just see that these positive charges that forms this reddish cloud must be massive. And also it explains why the atom is electrically neutral, because there is a cloud of positive charge. So this model has a very funny name, which is the plum pudding model, because you can think this is really a plum pudding. I mean, the electrons are really, the plums. And you have here this picture that was the proposal by Thomson. Okay. The electrons themselves can move in this cloud, but the important thing is that the positive charge is not concentrated in a region, but rather they are inside this cloud, okay, that form the atom. And they form a cloud that has roughly the size of the atom. Okay, so Thomson used to work at the Cavendish lab at Cambridge University, and his successor, Ernest Rutherford, started doing some experimental work where he was essentially throwing radiation, okay? So he was sending electromagnetic waves, or you can think of a beam of particles now, if you think of radiation as being composed by photons, against a material. So he had some radioactive source of radiation, and this radiation was directed to some material. And in particular, the setup that he used was the following. So this equipment here is formed by some radioactive source. In particular, he used radium. This emits radiation, and this radiation, is emitted in several different directions. And in order to select just one direction, he introduced this collimator here. So this is essentially a barrier that will not allow those electromagnetic waves, or let me call it just radiation, does not allow those radiation to escape from this region. So just this beam will pass through, okay? Now, this beam that was selected in a very particular radiation will hit a gold-made foil, okay? So this is a very thin layer of gold. And so you are hitting the gold foil with these beams of photons, and as we just understood by the Compton effect, this beam will be deflected, will be scattered to some direction, and I can place a detector in order to tell me in which direction this beam was scattered. Okay. This beam was made of alpha particles. You don't have to know the details about that, but the important part is that you are really sending radiation against a very thin layer of gold. Just to give you some details, the emitted alpha particles were emitted with this velocity here. So this is a very high speed. And the gold foil, this gold thin layer here, had the dimension of 10 to the minus 3 millimeters. And if you think about the atomic scale, this is just a bunch of layers of atoms, okay? So the particles are scattered and you measure them indirectly by a microscope. This is the setup of Rutherford experiment. Um, so this whole setup was placed in vacuum in such a way that these alpha particles would not collide with anything on the way. So the only obstacle they would encounter was the gold foil. Um, but of course, there is something that has to be considered, which is the following. The mass of these alpha particles that we are sending, um, they are much bigger than the mass of electrons. Okay, and because this mass is way bigger than the mass of the electron, you can think that uh, essentially these very massive particles will hit the electron and almost nothing will happen to them, because the electron has a very tiny mass compared to the alpha particles. So the alpha particles will collide with electrons and they will essentially not suffer any deviation from the initial trajectory. Also, if the model proposed by Thomson was correct, the plant pudding model, then because you have uniformly distributed positive charges, then these alpha particles would hit a positive charge, then another positive charge, then another positive charge, in such a way that in these random collisions, the net effect of that would be that essentially no deviation would be seen. So what Rutherford expected was essentially to see just very, very tiny values for this angle theta. Okay, and he had two assistants, Geiger and Marsden, and they performed this experiment, and indeed they did not find any big deviation from uh, the initial trajectory of the alpha particles beam. So they measured just very, very tiny values of theta. So they thought that, well, our assumptions and predictions are correct. I mean, the electron has a mass much smaller than the alpha particles, so they will not play an important role for the deviation of the alpha particles. And the positive charges, since they are uniformly distributed, they will not produce a net effect that is relevant. So, however, Marsden was a young researcher. Sorry, there is a question. What is the importance of the angle? You're going to see. I'm going to explain that. Marsden was a young researcher, and Rutherford and Geiger just decided to give to him a task, which was the following. Well, try to repeat such an experiment several times and see if by some reason you detect some large theta. Okay? And Rutherford did not believe that Marsden was going to find a big value of theta, okay, because of those reasons that I just explained. But it was a great surprise that, in fact, Marsden and with Geiger, they not only detected large values of theta, okay, so they really saw this beam being scattered to a large value, but they also saw beings that were backscattered. What I want to say about that? So you send a beam in the direction of the gold foil, and you would see some beam hitting the gold foil and going back. Okay? So they measured really beams that were hitting the gold foil and going back. And this was totally surprising because, as I said, this was a very thin layer of gold, and you had just electrons with very small masses compared with the mass of the alpha particles. And moreover, the positive charge of the atoms were uniformly distributed. So you do not expect that uniformly distributed charges would produce backscattering. Okay, so this is the result of the experiment. They found alpha particles beings that suffered very strong deviations from the initial trajectory, but also that were backscattered. And there is a question in the chat. Let me see. Please, can you come again to why you want to find the line? Okay, so actually, Rutherford did not believe that he could get large values of theta. And they only insisted on this experiment because Marsden was initiating his scientific career, and Geiger and Rutherford just said, well, do more measurements about this scattering and see, I mean, what is the largest value of theta that you can get. But they really expected that this was going to be a very tiny value. And they were completely surprised by the fact that they not only detected large thetas, but they also detected beings that were coming back to the direction of the collimator. Okay, so this was a total surprise, and it was absolutely incompatible with the atomic model proposed by Thomson. And with these, Rutherford was really thinking on how to explain that. How do we explain that these alpha particles can hit the gold foil and come back? Or
Hello, Andrew.
yes?
Please, did Thomson introduce the electrons? Did he also introduce the protons, or he just guess there is a protons or positive charged?
Okay.
That makes a atom neutral.
Okay, so Thomson discovered the electron, and he proposed an atomic model. So he proposed that an atom should be formed by electrons and some positive charges. Okay, but he proposed the model as being, let me just find my cursor. Okay, he proposed the atom to be like that. Okay, so far we did not. We are not talking about photons. Photons were proposed. Well, not even with this name photon, but these particles of light were proposed by Einstein, explaining the photoelectric effect. So Thomson discovered the electron and proposed an atomic model. Okay, and also I'm not using the word proton here. Okay, so of course, we know we learned at some point that those particles were protons, but at this stage, the only thing that they knew was that the atom should contain some positively charged particles. Okay?
Okay, thank you.
You're welcome. And there is another question. It's because the alpha particles meet other particles. So the point is that this is partially correct, but you see that when you throw the alpha particles, if they suffer a big deviation, just think about classical mechanics, right? If you throw a ball against, for instance, if you pick up a bowling ball, namely it's something very heavy, and you throw against a balloon, Well, the bowling ball will simply pass through it. I mean, it will not suffer any large deviation in its trajectory because the balloon is very light. Okay. But now assume that I have distributed some balls that are not balloons. I mean, some more heavy balls, and I throw the bowling ball. Well, when I throw the bowling ball, it will hit a ball here, a ball there, and so on. But in the end, the trajectory of the bowling ball will not be hugely affected. Okay. Now, collect all these balls to a very concentrated and dense region and throw the bowling ball. If the bowling ball now hits uh, um, this cluster of balls that you have created, since now this is a heavy and robust target, the bowling ball will hit that and will deviate considerably. Even worse, it might be that the bowling ball will hit this cluster of balls and backscatter, will come back. And this was the insight that Rutherford had and said, well, if I see those alpha particle beams that are being largely deviated or even backscattered, then I will assume that the positively charged particles are concentrated in a small region, okay? But this small region will contain a bunch of positively charged particles with a big mass, okay? So Rutherford changed the picture, which was now, what was the proposal that he made? The proposal is that now the atom is not made of a cloud of positively charged particles with negatively charged electrons here, but rather it will be made of a nucleus. So this is the discovery of Rutherford. He proposed the nucleus of an atom, which we all know this very well. We are very, used to this concept nowadays. But he said the positively charged particles are inside this tiny region that is called the nucleus, and the electrons will be flying around in a cloud of around this nucleus. And you see that this nucleus has a dimension, has a size of the order of 10 to the minus 12 centimeters, and this was estimated by Rutherford using Newtonian mechanics. And the cloud of electrons has a size that is 10 to the minus 8 centimeters. So the nucleus is way smaller than the size of the entire atom. Okay. Most importantly is the following. If you have, yes, the electrons are negatively charged. Yes. So if you have a cloud of electrons, and if you have Z electrons, so the number of you count how many electrons you have in the atom, and you count Z, okay? If you have Z electrons, then Rutherford said you are going to have Z positively charged particles in the nucleus, and the charge inside the nucleus is Z times the absolute value of the charge of the electron, okay? We already used this word before. E is the absolute value of the charge of the electron. So the charge inside the nucleus will be Z times E. And Z is what we call the atomic number. Okay? So for an electrically neutral atom, Z tells you how many electrons you have flying around in the electron cloud. Okay? So Rutherford discovered the nucleus of the atom and changed the picture by Thomson. Namely, we don't have a cloud of uniformly distributed positive charges, but rather we have a very tiny and dense nucleus with all the positive charges of your atom. Okay, so this was the big discovery by Rutherford, and of course this, as we are going to see either today or tomorrow, this has a profound impact uh, uh, in the construction of quantum mechanics, because the very fact that the nucleus exists will make the description of this model incompatible with classical mechanics. And there will be a Danish physicist called Niels Bohr that will fix that. Okay? So far so good. Are there questions?
Hello.
Yeah.
Please, the backscattering of alpha particle, is this because the heavy dense of positive charge or because the positive charge itself?
No, you see that it's not enough to have just positive charge, because in the Thomson model, you also have positive charges. But the fact that they are uniformly distributed is not enough to produce a huge deviation. Okay, so you really need positive charges and that they are concentrated in a small region.
Okay, that means that both of them are share the backscattering. Contribute
Both.
the back both
Yes,
the
yes, yes, yes.
okay, thank you.
More questions about that? So if this is not the case, I also remember that there was a question that I didn't answer before. I think it was this question by Elise. Do we consider energy loss as energy used to move electrons after collision about the Compton effect? And the answer is yes. The energy loss is the energy that's, I mean, you're not losing energy, but you're exchanging energy with the electron. You're giving energy to the electron to move. Okay. Grace said the nucleus contains positive charge. So the nucleus will contain positive charges. And as we know nowadays, there are also neutral particles inside the nucleus, which are the neutrons, but they didn't know that at that point. Okay. So it is just to say that inside the nucleus, you have positive charge. And this nucleus should be a small region. And there is a great question. Please, all of this is, what is the relation of that with quantum mechanics? Because I'm a little lost. That's a very good question. Because as I said, this model here, so far, I mean, we did not use any, let's say, any relevant concept that we have introduced the days before about the quantum theory. But as I'm going to say, this is important for the quantum theory because we are going to come back to this model and we are going to see that if you insist on the classical theory, this model is totally nonsensical. You have to introduce a quantum effect in order to make this atom something that makes sense. But I did not explain that yet. So if you are lost, take this as take a breath and wait for the next episodes. Okay, we are going to discuss that. So far, I just want you to understand from this discussion that the nucleus was discovered. Okay, and then we're going to see what is the impact of that for the quantum theory, or I mean, better saying, what is the impact of that for the classical theory and why we need quantum theory? Okay. Okay, so I hope I have answered the questions so far. All the questions. If I missed some of them, just let me know. Okay, now I want to move to another very important concept, and I want to do that in such a way that when we move to the discussion of the Bohr description of the atom, we have a complete picture. Okay, so we are going to move to a very important discussion, which is what is called the atomic spectra. Okay. Um, Now we are going to make a small deviation from our discussion and go back to Newton. Okay. So there is a very famous experiment that Newton performed that you might have heard about, you might not, but I hope to be self-contained here. So Newton did the following. He took a beam of white light, okay, and passed this beam of white light through a prisma. So this is essentially made of glass, and you can think that as uh, uh, these objects that, so to avoid the messy drawing, I just took this picture. So there is white light coming through. It passes the prisma, the glass-made prisma. Sorry? I should say prism and not prisma. That's actually a good point. I mean, now I'm confused. So it's oh, you are correct. I should say prism and not prisma. The prism, yeah. So you are correct. I should say prism, okay, and not prisma. Prisma. I'm using the Portuguese word actually. In Portuguese, we say prisma. So this is a prism. So maybe I should fix the notes. So this is a prism. So by sending this narrow beam of white light through this glass-made prism, Newton verified that the outgoing beam, so this was a narrow beam made of white light, and it went through the prism, and then you see that it becomes wider, okay? So it becomes a wider beam, and also made of several different colors. So when you pass through the white light through the prism, it opens up and you see different colors. Actually, you see the colors of the rainbow. So you see that you can detect colors from reddish to violet. And an important point is the following. Maybe if you're not familiar with the theory of electromagnetic waves, you have to understand that light of different colors is nothing but light of different frequencies. Or, in other words, it is just light of different wavelengths. So when you see colored light, I mean, it is still light, but with a different frequency. Okay? Okay, so what Newton understood was that white light was made of a superposition of light of different colors, namely of light of different frequencies. Okay? So when you decompose a radiation or light into the different colors that compose the radiation, you are making a spectral decomposition of that. So when you say that white light is made of colored light, you're saying that the spectrum or the spectral decomposition of white light is this collection of lights of different colors. Okay? So, so it's written here, as I said, different colors represent different frequencies. So every time that I say color, you can mentally exchange it by frequency or wavelength. So different colors you associate to different frequencies or different wavelengths. Okay? So Newton understood that white light was made of a superposition, namely a mixture of different colors of light. How can we get white light? Well, you can just so when you say that a given light ray has a well-defined frequency, then you are just saying that you have made a selection of a specific frequency. But of course, you can produce a light ray that contains a mixture of frequencies of different light rays, and this will give you white light. You can also think, if you want, as a light coming from the sun. Okay, you can just take light from the sun, but as we're going to see, this is subtle, and this is the next point that I'm going to discuss. So Newton realized that throwing white light, you could decompose the white light in different in this spectral representation, and you see that you change the colors in a continuum way. So there will be no dark spot here. So in this range coming from here to here, all spots are illuminated, if you wish, by a different color. Okay. Now there is a second experiment that was made. Okay, can we use another prism to get the... Okay, so you see that if you focus all these beams towards a prisma, then you're going to see the opposite thing, the opposite picture. Yeah. So you can focus all these beams towards a focal point and produce white light. Yes. Now a German physicist called Fraunhofer. Sorry, what is that? So I didn't get this principle of... Yeah. 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 You're correct. Okay. So Fraunhofer did a very similar experiment that Newton did, but instead of picking up white light, artificial white light, he took white light from the sun. So he just, passed through a prism, white light emitted by the sun. Okay. So I should erase again the A here because I wrote prisma. So prism. And well, he did that, and he saw a result that was similar to Newton, but with a very important difference. So what he verified was that some colors, okay, so you see here that I have this spectrum going from these more violet colors towards red colors. You see that, so here is the limit of the visible spectrum, so our eyes are not able to detect all colors, all frequencies. So you see that from here to here, you have these black lines, okay? So these dark lines in particular spots. Okay? So what happened was that for very well-defined wavelengths or frequencies, when Fraunhofer passed sunlight through a prism, there was dark lines. Okay? So he didn't see a continuum of light, of different colored light from violet to red, as Newton did. Okay? These dark lines that we see in the spectral decomposition of the sunlight is what we call Fraunhofer lines. Okay? So what Fraunhofer realized was that, I mean, it was missing some colors in the spectrum of the sunlight. And this is, well, you have to explain why. I mean, you have to explain why for very specific, wavelengths, these colors are missing. Well, you can say, well, let me perform again the experiment by Fraunhofer and see what happens. And we are going to see that exactly the same dark lines appear. So it's not a particular problem of the region and the time that Fraunhofer performed the experiment, but this is a property of sunlight. Okay? So it took a while to understand why these colors were missing. And actually, what it was understood was that when, the core of the sun emits light, light has to pass through the sun atmosphere. So there is an atmosphere in the sun. And the sunlight that is produced in its core, which is white light, has to pass through this atmosphere. But this atmosphere is made of some chemical components. It's made of some atomic species. So when the white light passed through this atmosphere, we have learned and discussed in the previous lectures that atoms can absorb radiation. Okay? And what happens is that the white light produced in the core of sun, when it passes through the sun, the solar atmosphere, these atoms that are part of this atmosphere absorb some specific radiations or specific colors of the spectrum of the sunlight. So I will repeat. When the core of the sun produces white light, it passes through the sun atmosphere, and the atomic species that live in this atmosphere will absorb some colors of the radiation. And when this resulting sunlight arrives on the Earth, then we detect the spectrum of the sunlight, but of course, some specific frequencies of the sunlight were absorbed in the solar atmosphere. So we don't see them. They were absorbed. Okay? And as I said, this is at very specific values of the wavelength. So this spectrum here that shows let's say, the frequencies that compose sunlight, or if it's not produced by sun, but any other source, this the composition that will show to you these dark lines against the colored lines is what we call the absorption spectrum. So you see that here I'm showing to you all the frequencies that are emitted by the sun, but those that are absorbed by the solar atmosphere. So this is an absorption spectrum. Okay? So this is a very important concept. Okay, so I think I will stop for the break and then I come back to this discussion because I don't want to rush now. But the key message is, if you want to reproduce the experiment performed by Newton using sunlight, you see not all the colors that Newton saw, but you're going to see all the colors with some dark lines that are precisely those colors that were absorbed by the solar atmosphere. Okay? And this is what Fraunhofer saw. Okay? So I hope this is clear. We can stop now for the break. And then after the break, I will explain a bit more of that, and we can discuss the exercises about the photoelectric effect. So we come back in 10 minutes.